Okay, so the last little bit of this is going to talk about collision theory. So now what we're going to do is we're going to look at the molecular level and see what's happening at the molecular level. Rate constants vary with temperature, so you might have noticed on some of the previous ones it said here's the rate law at this temperature. It would change if we had different temperature, of course, because reactions go faster at higher temperatures in general. But we're gonna talk more about collision theory to explain that. So let's make a few assumptions. Collision theory, what do we think is happening at the molecular level? We're going to assume that for a reaction to occur, the reactant molecules have to collide. They have to collide in the proper orientation, and they have to collide, I'll do it that way, and they have to collide with enough energy to break the chemical bonds. Okay, so all of this has to happen. The minimum amount of energy required for two molecules to react is called the activation energy, and we mentioned that earlier in the slideshow. So in order for a reaction, it has to have just enough energy to get over this minimum. That's called EA, activation energy, and we're going to see it graphed in just a minute. And so what's happening is we have two molecules colliding, and right at the instant where they collide, we're in the transition. And so the transition state theory says that as these two molecules collide, we have what's called an activated complex. And that's at the transition state when my new bonds are being formed and my old bonds are breaking. So that's called an activated complex. Everything's stuck together, and it's called the transition state. So again, the activated complex is just an unstable grouping of atoms that actually can break to form the reactants back, or can rearrange and break off to give us the products. So it's sort of the highest energy, and it's where it's just transitioning from reactants to products. A simple analogy would be the collision of three billiard balls on a billiard. So if we shoot this white ball, and these two are kind of stuck together, those two balls are coated with a slightly sticky adhesive, and then we shoot another ball at it, and the white ball is also sticky, so I guess otherwise they're not going to ever stick together, but you get the idea. This is going to stick, and so the white ball hits the red ball, and it's going to be enough energy for the red and yellow ball to break, for the yellow to break off from the red. So they're going to collide. At the moment of collision, that's our transition. All three spheres are joined at that instant of impact. That's called the transition state complex, or sometimes the activated complex. The incoming billiard ball is going to stick to the red one probably, and it's going to provide enough energy for the yellow one to leave. And so there's a new pairing, there's new products. If we repeated that over time, some collisions would be successful, others wouldn't, either because maybe the white ball didn't ever hit the red ball, maybe it didn't hit with enough energy, maybe it hit the yellow side and it wasn't enough to kick the red ball off, maybe the improper orientation. So many collisions occur that don't result in products, that they're not considered successful, but many do. We could compare the energy we provide to the billiard ball as the activation energy. If that billiard ball comes in and has enough energy to break off the other one, it's kind of gotten over the hump. It's had enough energy to make this reaction go. And I use that term, getting over the hump, and you'll see in a minute why. All right, so what we're going to do is graph, another graph. We're going to graph the formation of the transition state. In order to graph it, we're going to put time or reaction point in the reaction on the x-axis, and we're going to do potential energy on the y-axis. And we'll look at, on the next slide, illustrates an endothermic reaction, so where you have to put energy in to make it happen. Note that the forward activation energy is the energy necessary to form the activated complex. I'll show you that in a minute. And delta H, which is the heat of the reaction, is the net change in energy between reactants and products. So let me show you the slide. So, all right, so here's the energy. So this is potential energy. How much energy do we have? We have the energy of the reactants. They're going to have to increase energy to get over this hump. Right here at the top is our activated complex, or our transition state. And then after the transition state, notice that the energy comes back down, and now our products are at a new energy. So this is the energy of the reactants. This is the energy of the products. And what I want you to notice is delta H is always products minus reactants. So this is our delta H. It doesn't have anything to do with this hump. So it's always final minus initial. In this case, remember I said it's an endothermic reaction, so that means heat is being put in. So that's why our products are higher energy than our reactants. So delta H is positive in this case because we had to put this much energy in for this reaction. Now the EA, notice I like to draw it over here from the start to the top of the hump. This is the activation energy. So this is how much energy you need to get to the activated complex in order for it to break apart and get back. So you always have this highest, the activated complex or the transition state is always the highest energy. The activation energy is always from the start to the top of that hump. And then the overall heat of reaction is always final minus initial. So delta H is always going to be less than EA because you have to come back down. So again, EA for the forward reaction is from the start, the energy of the reactants, up to the energy at the complex, and that's why I call it getting over the hump. And then our delta H is over here. Now if we look at this reaction from the reverse, if we went in the backwards direction, Cl plus NOCl, actually to get over the hump, this would be EA, this would be the activation energy needed for the reverse reaction. And so if we started with NOCl and Cl, we could actually create NO and Cl2, and the activation energy would be this, and would be 2 in this case. The delta H, notice, would be the same, but because it would be final minus initial, it would be negative 83, so it would be given off if you're going in this direction. So in the progress of the reaction, it's positive, it's endothermic. So that's called a potential energy diagram. If we wanted to see what an exothermic reaction, you would see that the products are more stable than the reactants. And so the next slide will show us that. Again, we see that the forward activation energy is still required. So there's still some energy that's required to get over the hump, even for an exothermic reaction. And so let's look at that. Okay, this is an exothermic reaction. And notice that our reactants, here's the energy of our reactants. The activation energy, again, is from the energy of the reactants up to activated complex. So this is EA. They just did it from here to here. They're just showing it over here. I always like to draw it in here because it's to the top right there. So that's EA. And then delta H again is always final minus initial. So it's always the distance between the reactants and the products. In this case, because the products are lower than the reactants, delta H is negative. The EA for the reverse reaction, if we're going in that direction, is much larger this time to get over the hump. And going backwards would be an endothermic reaction because it would be higher here. But in this case, this is exothermic because we're reading it from left to right. A couple of other things to note. I think they're coming up on the next slide. I'll mention them if not. Yeah. So let's look at these two reactions. Are they endothermic or exothermic? So they should be, both of them are exo, because notice that the products are lower than the reactants in both cases. And actually, if you look at these two, both of them have a very similar delta H, because that's just the distance between the bottom line and the top line. So actually delta H is going to be the same. So they're both delta H. But what's the only difference between these two? It's the activation energy. So this has an activation energy that's smaller than this one. So both are exothermic. The second one has a higher activation energy. Would you expect that reaction to be slower or faster? If both reactions are run at the same temperature and have the same orientation requirements, which one would be faster? Well, it will be the one that has the lower activation energy. All things else being the same, the smaller the activation energy, the faster. So I'll put it to that one. All right. Let's talk about the temperature, the effect of temperature. We've discussed the effect of reactants. Remember some things about the effect of the reactants. They have to be able to come together. So the closer they are, the faster they react. So if they're in different phases, the contact is important. And so more surface area will make it faster. Concentration, the more molecules, the more collisions in general. And now let's talk about temperature. So reaction rates ordinarily increase with temperature. It's pretty rare not to. Remember, what is temperature? Temperature is just a measure of the average kinetic energy. If you increase the temperature, the molecules are going to move faster. So increase in the temperature means higher kinetic energy and an increase in the average speed. They're not all going the same speed, but the average speed increases. This increases, so it's two things. It increases the likelihood that a larger fraction of molecules have enough energy to get over the hump. So more molecules have enough energy to make it over the hump. And it also increases the number of collisions. And more importantly, the number of successful collisions that lead to product formation. So that's why, so it's two things. Not only are there more collisions, there's more energetic collisions, so more molecules have enough energy to get over the hump. So we can look at what's called the Arrhenius equation. And the Arrhenius equation relates the activation energy and the temperature of the reaction to the rate constant of the reaction. So the Arrhenius equation expresses the dependence of the rate constant on temperature and on activation energy. So both things. A is called the frequency factor, and it's actually related to orientation and frequency of collisions. And the rate constant, K, of course, is dependent on the activation energy and the temperature. So K is just the rate constant. And with a bigger rate constant, generally the better the reaction. So what are these graphs telling us? This graph here on the left, what this is just a kind of a description of the number of molecules. So this is number of molecules on the y-axis and kinetic energy. And so, like, if this is your average kinetic energy, so the average speed that your molecules are moving. Some are moving faster, some are moving slower. The area under the curve represents how many there are. So obviously there's a lot up here. There's very small moving very slowly, and there's a small amount moving very quickly. But notice one thing. So this is just telling you how is the activation energy affect the rate of the reaction. Well, if you have a low activation energy, in other words, a low hump, Then you have more molecules that have enough energy to get over that hump. So they're showing you the stripes all the way over in green, all of this. With a low activation, you have all of these molecules that have enough energy. However, let's erase that. However, if you have a higher activation energy, you only have this much that has enough energy to get over the hump. So more molecules have enough energy at lower activation energies. So we know that the reaction rate is dependent on activation energy, because the higher the activation energy, the fewer molecules can make it over. So that's how the rate law constant is affected by EA. Now what this equation is telling us has to do with increasing temperature. So notice that the EA stays the same because it's the same reaction. Oh, here, the purple, let me draw purple. So this would be, you know, if EA was higher, that would be fewer molecules would have enough energy to get over that hump. Okay, back over to this equation. So this time they're not changing the EA, but they're just looking at what does temperature do. So notice that the red line is for the lower temperature, and they're showing you, this time I'll use purple, at the lower temperature, this is how many molecules have enough energy to get over the hump. But at the higher temperature, this whole thing, so notice that your average moves up. So if you increase the temperature, your average kinetic energy increases, whereas this one is your average for the lower temperature. So not only are all molecules moving faster, now you have, go back to the green, now at the higher temperature you have a bigger percentage of molecules that have enough activation energy to get over the hump. So both of those things are true. The most useful way to use the Arrhenius equation is in this logarithmic form, and since we're all into logarithms now, this shouldn't be too difficult. If you take the natural logarithm of both sides of the Arrhenius equation, we have this. And similarly to what we did before, if we plot, should have written it the other way, but if we plot 1 over t versus the natural log of k, we should get a slope of negative EA over R, and R is just that gas law constant. So the slope is definitely related to the activation energy, and the y-intercept is just the natural log of A, and A, just remember, A just was the frequency factor. The important thing here is how can we find the activation energy if we know temperature and K? And so this is the best format. The natural log of K will equal to negative EA over R X, or negative EA over R 1 over T. So if we plot 1 over T on the x-axis versus natural log of K, we should get a slope that's equal to negative EA over R. And that's probably the most important part. So here's an example. I don't know what it comes from, but if you look, if we plot 1 over T on this axis versus natural log of K, we get a straight line. This is just showing you that what if you, a more useful form, if you look at 2 points, so on that previous slide, if you just pick 2 points, T1 and T2, natural log K1, K2, do some magical rearrangement of these equations, because notice that this will actually cancel out. And if we do some rearrangement of these equations, we get this equation, which is the Arrhenius equation at 2 temperatures. I know you don't have to worry about how we rearrange this, just that it's rearranged. So notice that if you take the natural log of K2 over K1 and 1 over T1 minus T2, we can solve for EA, because R, again, is just our gas law constant. The only thing you have to be careful about is units, because R is 8.31 joules per mole Kelvin. So you want to make sure that that means your EA will be in joules. All right, so let's look at an example. The rate constant for the formation of hydrogen iodide is, so K, so here's K1 at T1. At 600K, it's 2.7 times 10 to the minus 4. And at 650K, T2, let's do that in another color, T2, the K value is this, K2. And what they want you to do is find EA. So now it's just a matter of plugging this into the equation. Even though it looks scary, it's not so bad. So we plug K2 over K1, EA over R is just 8.31, and then T1 minus T2. So I took the ratio, 3.5 times 10 to the minus 3 divided by 2.7 times 10 to the minus 4 is 1.30 times 10 to the first, or 13. Make it easier. The natural log of 13 is 1.11 equals EA over R, and then if you do this 1 over 600, figure out what that is, minus 1 over 650 to make sure that T is in K, in Kelvin. So this equation simplifies down to that. So 1.11 equals EA over 8.31 times 1.28 times 10 to the minus 4. So if we just rearrange and solve for EA, so just rearranging for EA, you can see that EA equals 1.66 times 10 to the 5th joules. And that's the same unit that R was. So it's actually joules per mole. If you wanted to convert that to kilojoules, that'd be 1.66 times 10 to the 2 kilojoules. Divide by 1,000. But it didn't ask you to, so don't worry about it if you don't want to.